Alrighty, today we are going to talk about complex power. So I guess the first thing I want to do is ask you guys, I guess, how comfortable you felt about this topic when you covered it in Circuits 1. Anybody care to venture anything?
Wasn't my favorite.
Wasn't your favorite? Okay, but like, how did you feel? Do you feel like you understood the material, or do we need to like get into the meat and potatoes and really review?
Probably a little bit separate from power factor correction.
Power factor correction is a very small part of this.
Power factor correction. No.
No clue.
No.
Okay. All right. All right. So we are going to talk today then about complex power, which is actually a very, very important and useful quantity if you go into the field of power engineering, which some of you will probably wind up doing. Go work for Entergy or AEP SWEPCO or Southwest Power Pool or something like that, okay? The complex power as a quantity is so important because it succinctly allows us to determine really all of the different power quantities about a particular load impedance or what a source is providing or something like that without doing a whole heck of a lot of work, okay? So if we have a generic load impedance Z, where just pictorially, this would look something like this. It has a phasor voltage drop V across it and a phasor current I flowing through it. Let us just quickly state our phasor voltage V will be Vm angle theta V, and our phasor current I will be Im angle theta I. The complex power is defined to be S is equal to 1/2 V phasor times I phasor conjugate, where S is a complex number. Now, carrying around this extra factor of 1/2 can get pretty annoying pretty quickly, okay? So instead, we are going to be working in a new domain. So I'm going to call this guy here our frequency domain relationships. And we are now going to be working in what I'm going to call the RMS phasor domain. All right, so to denote that we are in the RMS phasor domain, I choose to, instead of putting a bar over everything, put a little squiggly hat on top of it, letting me know that this is representing a sinusoidal quantity that is an RMS value. And this, by definition, is simply the phasor voltage divided by the square root of 2. So it has some RMS magnitude with the exact same phase angle. And I can do a similar definition for RMS phasor currents. Like so. This allows us to write our complex power as the RMS phasor voltage V times the complex conjugate of the RMS phasor current I. So our complex power is simply the multiplication of 2 simple complex numbers, where this is in the RMS domain. Since complex power is the product of a voltage and current, it should seem like complex power should be measured in watts. However, that would be arbitrarily confusing, okay? So power engineers developed their own unit for this specific quantity, and it is called the volt ampere. So the volt ampere is the unit of complex power. Dimensionally, it is identical to a watt, but if you're talking to another electrical engineer and he mentions something in volt amps or VA, that means that he's specifically talking about complex power or apparent power, which is the magnitude of complex power, and we'll be talking about that shortly. So right now, we are treating S as a complex number, which has obviously some magnitude and phase angle. Sometimes we only care about the magnitude, but that's obviously just going to have the same units. All right. So if we substitute in our RMS phasor expressions for V and I, what we get is S is equal to VRMS IRMS cosine theta V minus theta I plus J VRMS IRMS sine theta V minus theta I. So this is just using Euler's identity. And we can say that this is equal to VRMS multiplied by IRMS time, or with an angle of theta V minus theta I. So we have a rectangular representation of complex power and a polar form representation of complex power buried inside this equation, right? So just to be clear here, this is our rectangular form. This is our polar form. I'm pointing this out because your calculator can give you both of these back. So just to give you a heads up. So let's first look at the real portion of the rectangular form of S. The real portion of S is given by VRMS IRMS cosine theta V minus theta I. Well, this is identical to Vm divided by the square root of 2 times Im over the square root of 2 times cosine theta V minus theta I is equal to 1/2 Vm Im cosine theta V minus theta I, which we've seen before, right? So the real part of our complex power is simply the average power that we were already computing for the last couple of days, all right? So the real part of our complex power is simply P average, which we know has units of watts. The average power represents the portion of the complex power that can perform work on a load and is measured in watts, as we've mentioned, okay? So this is a critical part, all right? So for example, let's take these lights in this room, okay? Now we know that the lights in this room, although they're not connected by any cord or anything like that that we can see, they are powered off of either a 120 volt RMS or 240 volt RMS signal somewhere in this room within the electrical wiring of the room, right? So it is an AC signal, okay? The real part of that AC signal or the AC power that is being delivered to these lights is what's actually allowing them to light up, okay? There's also going to be some very, very small portion, which is going to be called the reactive power that we'll talk about in a second, that really doesn't do a whole heck of a lot, at least as far as the lights are concerned, okay? So if we look at the imaginary portion of our complex power, we have VRMS times IRMS times the sine of theta V minus theta I. This is more commonly referred to as the reactive power Q, where Q has units of volt amperes reactive, or VARs, okay? The reactive power represents the portion of the complex power that continuously flows back and forth between the source and the load in a steady state sinusoidal system due to the presence of capacitors and inductors. So if we were to look at the instantaneous power absorbed by a capacitor, for example, this is T, this is the power absorbed by a capacitor as a function of time measured in watts. The power would look something like this. Okay. We're looking at the instantaneous power here. 1/2 Vm Im cosine twice omega t plus theta V plus theta I, which is the same as VRMS IRMS cosine twice omega t plus theta V plus theta I, okay? This is power. Everywhere above that horizontal time axis shows where that capacitive load is, or inductive load, is absorbing power. And everywhere below that horizontal axis is everywhere that that load is supplying power. So we see that for a fully inductive or fully capacitive load, we are always either absorbing, we're absorbing power for a half cycle and then sending it back to the generator the next half cycle over and over and over again. So this part of the power is completely incapable of doing any work whatsoever, because it's just sent or received and sent, received and sent, received and sent over and over and over again. So a common question that I get asked is, if reactive power just represents power being transferred back and forth, then why have it at all, right? What is it used for? Reactive power is used in electricity distribution and in electrical machines. In electricity distribution, reactive power is injected or absorbed to maintain voltage levels when demands on the power change. So they are a form of temporary energy storage because they're based fully on capacitances and inductances, which we have seen throughout Engineering 221 and this class are short time energy storage devices, right? So if we need to generate a little bit more voltage so that we don't have a brownout or something like that, we would switch a capacitive or inductive, a large capacitive or inductive load into the grid, which will make those voltage levels rise and avoid having a blackout condition. In a electric machine, the reactive power is what's used to create and maintain the magnetic flux needed for rotation, right? So in a motor, particularly an electric motor, It's got a rotating magnet called a rotor and a stationary magnet called a stator. And it spins around in either a clockwise or counterclockwise direction, depending on the phase sequence of the motor, if we're talking about three-phase stuff. Well, as the rotor spins into phase with the correct part of the stator, that causes the output voltage to be higher, which generates more magnetic flux, which kind of keeps the machine going. So as it passes through, then it'll go to the next one, its flux will drop down, it sees another one, everything lines up correctly, the flux jumps back up, which means the voltage across it is at its highest. So it's trying to maintain effectively a constant voltage across the different terminals of the motor as it spins round and round and round. And that flux is generating a torque, which is causing the motor to spin. All right. If we look at the magnitude of the polar form of the complex power, we simply have VRMS times IRMS, and we call this the apparent power, okay? So that's S with no bar across it because it just represents a scalar quantity. We might also see it represented, some people just do AP for apparent power, and it is measured in volt amperes as well. Apparent power represents the total power absorbed by a load without considering phase differences between the voltage and current waveforms, okay? So how many of you have ever, well, probably none of you have ever bought a generator, but some of you may have bought a uninterruptible power supply for your computer or something like that. One of those big black boxes, those big heavy black boxes that you can plug your computer into, and if you suffer a power outage, it'll keep your computer running for like 15 or 20 minutes or something like that, depending on the size of the box. Anybody heard of such a thing ever? Okay. So when you buy one of those, it has two figures of merit, one of which is the average power. So it gives you some number in watts. And then it also has a rating specifically for the applied power. And the reason that it has that is because your computer or whatever you're plugging into it might have some form of induction motor in it, like in a fan or something like that, that is going to require some reactive power in order to work. So you size things like that based on the apparent power. If you are designing so I was going to say a home, but that's not really right because the overwhelming majority of the loads in your home only consume average power. But if you were working at a manufacturing plant or something like that, and you were trying to set up the distribution system, you would design everything towards an apparent power. Actually, I take that back. In your home, how many of you have ever heard of the concept of ampacity? Probably next to none of you. Okay. So ampacity is the technical term for the amount of current a wire can safely handle, okay? So for the wires that feed the plugs in this room, they have to have an ampacity of, let's see, what's 15 times 125%? 15 plus 1/4 of 15 would be, yeah, around 18.75, something like that. Or, yeah, they have to have that amount of ampacity to safely carry currents. Okay, it's at 125% because that's what the National Electronics Code tells us that we have to do to maintain a proper safety factor. The ampacity depends on both the material of the wire. So in most modern systems, it's just copper wire. It might be braided or stranded or something like that, but it's usually just copper wire. And it also depends on the insulation material. I'm getting away from my original point. Whenever you're setting up or choosing the type of wire in a home, in a circuit, or anything like that, it's always based on the apparent power because the apparent power tells you that the absolute maximum that the current will ever be, because it doesn't take into account phase differences or anything like that that would cause things to cancel each other out. So when you design electrical systems, you're always designing to apparent power specifications, okay? Because that is the absolute worst case scenario bundled up into a nice, neat little number. All right. The last portion of our big expression that we have yet to look at is the angle or the argument of the polar form. So the argument of our polar form of complex power, theta V minus theta I, is also expressed as theta S, and this is known as the power factor angle. Okay. The power factor angle is defined as the angle by which the voltage leads the current in the load. And so now we're going to spend a couple of minutes talking about power factor, because this is one of the most critical pieces of complex power. Have any questions thus far? Yes, sir. Sure.
What are the differences between like wire and having a singular solid core?
So a solid core of wire can carry more current before it melts and all that kind of good stuff. The biggest drawback of it is it's mechanically much more brittle, right? So you can't bend it nearly as easily. So running it through conduit and stuff like that is a lot harder. You have to be careful about the radius of your bends, because you can break it more easily, or you can cause deformations, which will change the cross section of the wire. So if the cross section of the wire gets narrower, it means that that portion is going to get a lot hotter because it has more resistance to the current flow, which could potentially burn out your insulation, cause shorts, set fires, all that kind of good stuff. Yeah.
Started in physics so we're talking like 2 weeks ago, we were talking about cross-sectional area and how that affects resistivity. And
yeah. So if you're talking about just a general, I mean, this is a complete aside, and this was covered in engineering 121 as well as 221, hopefully. But the resistance of anything really can be determined as a function of its geometry as well as its material. So the resistance of something is rho L divided by A, where rho is its resistivity, L is its length, and A is its cross-sectional area. And because of the inverse relationship between resistivity and conductivity, this is L over sigma, where sigma is conductivity. Okay. You won't ever need to know that for this class, but it's just a general kind of thing that you probably should have heard of by now. That's a terrible looking sigma, but I can't draw it any better. So yeah, so if you have a solid piece of wire, it's going to have a significantly smaller cross-sectional area, which means it's going to save you space. But the issue that the largest issue that you're going to have is its ductility and weakness and all that kind of stuff. Whereas if you use a braided wire or a stranded wire, you're breaking up the amount of current that's flowing through each individual strand, making it much, much, much smaller, but it occupies significantly more space. But it's considerably more flexible. So like some of the wires that I work with are what are called 1-knot and 4-knot wires. And so they're about this thick, and they are made of sections. So they're like a whole bunch of strands combined in a little wire, and then a bunch of those little wires are bundled together in a big wire. The wires that I use are called DLO because they are for diesel locomotive generators, technically. So probably a lot of you guys don't realize this, but most trains nowadays, even though they have a diesel engine, the diesel engine is just used to power a generator, and then that generator uses electricity to cause the wheels to turn and all that kind of stuff. Those particular cables need to be very, very flexible, and so that's why they're constructed in that particular way. And that's the kind of standard cabling used in lithium-ion battery energy storage buildings around the world right now. So, because of its flexibility, because you need to be able to route it in weird ass places. So, all right, that's enough, I guess, an aside from me. So let's circle back around to power factor. All right, so the power factor is a measure of the efficiency of power transmission to and from the network. Mathematically, our power factor is defined as the average power, P average, divided by the apparent power, S, or alternatively, we can express it as the cosine of theta V minus theta I. All right. Power factor values range from -1, which means the network is supplying apparent power at 100% efficiency, to +1, which means your network is absorbing apparent power at 100% efficiency. Typically speaking, we are going to be looking only at absorbed powers in this class. So the only time we would ever look at a supplied power would be for a source. And so I just want to make sure that we're all kind of on the same page. Oh, sorry, I thought I heard something, but you were blowing your nose. That's okay. So if we had a simple system, like we had voltage source Vs, which to me at this point would represent two prongs off of a transformer or something like that, okay? Then we would have a transmission line system. I'm just going to call this TL for now. We'll get into it in much more detail later. And then over here, let's say that we have a motor. Okay. We would expect an induction motor to be operating at a power factor of something around 0.7 lagging. It could be higher. So like the fans here in this room, when they are set on speed 3, they're drawing the most amount of power, which means that that induction motor is doing the most amount of work. And so we would see that the power factor is actually probably somewhere closer to around 0.6 with the speed set at 1. The reason why I know this is because senior design projects, some jackass always wants to measure power factor. It's boring the hell out of me because it's done every year. But they always wind up just taking fans from around the building and measuring stuff. And so at speed 3, it's somewhere around 0.6. At speed 1, it's somewhere closer to 0.9. So it's a moving target depending on how fast the motor is rotating and how much work it's trying to do and all that kind of stuff. There's actually going to be a power factor associated with the transmission line as well, because you guys may not have learned this yet, but you probably will in your physics classes, and if not, you'll definitely learn it in your electromagnetics classes. But a wire in any closed network also exhibits some inductance, okay? So we should expect that our transmission lines portion also operates at a power factor. It's going to be somewhere really close to 1, but it is also going to be lagging because of its inductive nature. So we would say then that our source we'll have a power factor, hopefully somewhere, and I'm just making up a number here, because it depends on the size of the motor and all that kind of stuff. Probably somewhere around 0.9 lagging. Well, the assumption that we've made here is that our motor is absorbing power, our transmission line is absorbing power, source is supplying power. But if we were actually dealing with everything absorbed, we would see that the power factor of our source should really be negative 0.9 lag. Okay, I typically don't care about the sign. I word my questions in such a way to where we always look at the power factor of a source as it's supplying power. But I want you to fundamentally understand that if you ever get a negative value, that's perfectly okay. It just means that it's supplying. Okay, probably won't happen in this class, but if it ever happens, there's no cause for alarm. That is perfectly within the bounds, right? It's based on a cosine function, which can range from -1 to +1. So if it ever gets negative, there's no reason to freak out. All right. So when a load is operating at a power factor of less than 1 in magnitude, it means that the source is being required to generate more than the minimum volt amperes necessary to supply the required average power needs of the load. Okay, so if the power factor is 1, that means that the average power and the apparent power are identical. You're operating at 100% efficiency. If the power factor is less than 1, then that means you have introduced some inefficiency to the network, which means the network has to supply some reactive power as well to meet with the demands. This is where I was talking about where apparent power becomes important in the design process, right? Because if you have a load that is operating at a power factor of 1, and it requires, let's say, 36 watts of average power, and the voltage is 36 watts of average power, and it requires a voltage of 12 volts RMS to operate, then you know that you only need to design your system to be able to handle a current of 3 amps RMS, which is pretty trivial, right? But if you have that same thing and it's operating at a power factor of only 10%, then really you're going to have to design your system to be able to handle something like 40 amps of current, because that's how much inefficiency you've added into the system. Okay, so that's where apparent power and power factor come in the design process. And I'm going to give you guys a problem on your exam about that. It's very, very trivial. Don't worry about it. Okay.
So you always want to make
as close to 1 as possible. From an efficiency standpoint, did you guys do the labs in 221?
We talked about practically improving your power factor, where you kind of want to aim for like 0.95.
Yeah. Okay.
Because if you could overshoot.
Yeah. So that is something that I wanted. Yeah. So if you actually did the lab in 221, which it sounds like you guys might not have done, that's okay. You had a simple system containing a resistor and an inductor, and then you place in parallel with that a capacitor. The capacitor is there to improve the power factor of the system. But if you put too much capacitance there, you'll actually overshoot and wind up with a leading power factor, which means the current is leading the voltage. There's nothing particularly wrong with that as long as the magnitude of the power factor is between 0.95 lagging and 0.95 leading, you're pretty much good. Did you guys talk about why power factor matters other than the efficiency or anything like that? Okay, so let's talk about making the power company happy. Okay, so the power factor, as I said, is a measure of the efficiency between the average power and the apparent power. Well, the average power is what you as a consumer pays for, and the apparent power is what the power company pays to create, okay? So meaning if they have to supply a large amount of apparent power, that means that they have to purchase and burn more coal or put more wear on their hydroelectric turbines and stuff like that in order to generate that power. They don't like having to spend more money and not getting to charge you any more money for the part that you use, right? And they also have to figure out a way to offload that reactive power as well, because it's temporary energy storage, not permanent. So they have to be able to get rid of it in some way, shape, or form. So what the electric distribution companies will do for very large scale manufacturing plants and stuff like this isn't something you'll ever have to worry about as just a homeowner or anything really, unless you have shit tons of conveyor belts in your house for some reason. But for a large scale industrial consumer at a manufacturing plant where they have a lot of induction motors running fans for cooling systems and conveyor belts and stuff like that, they have to keep their power factor above a certain minimum value or else they get a fine, right? And so what they do is employ a factor called power factor, or a practice called power factor correction, which involves putting a capacitor in parallel with their distribution system in order to make it look like the power factor of their whole system is on the up and up. And the power factor is higher than the minimum threshold, meaning they don't get those fines. So anyway, so the reason why increasing your power factor makes the electric company happy is because they don't have to pay more money to supply it to you. It's really that simple. All right. So as you've noticed here, power factors are classified as either lagging, which is all we've talked about right here, or leading. So we can mathematically describe this as if our angle theta s is between 0 and positive 180 degrees, we have a lagging power factor. And if our angle is between negative 180 degrees and 0, we have a leading power factor, right? A power factor of 1 is neither leading or lagging. That's because it means that the load is purely resistive, and a power factor of 0 is also neither leading or lagging. This would be for a purely capacitive or purely inductive load, okay? All right, any questions about power factor before we move on to a graphical representation that ties all this stuff together? Yes, sir. Yes, absolute worst thing, because that means they are generating power that you are paying nothing to consume, because none of it is doing any work that would show up on a watt meter, right? The power meters at your home is a watt meter, which literally just measures average power. Technically, it measures the energy, which is just average power times time. But if your home were somehow able to work off of purely capacitive and inductive loads, then you could get everything for free. They wouldn't distribute to you, but you could do it.
So washing machines?
So a washing machine wouldn't even be fully inductive, right? So a washing machine, it definitely does have an induction motor in it. That's what spins the tub around, or the agitator, or whatever the hell you want to call it, depending on how old your washing machine is and all that kind of stuff. But that electrical motor is comprised of, wires and things like that, which have a finite resistance. Also, it has a control board, which has a simple DC circuitry and all that kind of stuff. So even if it was a terribly inefficient washing machine from an electrical perspective, it would still have some small average power load associated with it. Same for a dryer. A dryer would actually likely have a higher average power load associated with it. The reason why I say that is because while it's definitely got an induction motor to spin the clothes around and all, or tumble the clothes and all that kind of stuff, the heat that's generated by at least an electric dryer is a simple resistive heater, much like you'd see for a space heater, and then a small fan that just blows the heat off of that nichrome wire into the drum to dry your clothes. So heaters are typically have a larger average power load because of the way that the heat is generated. If it's a gas dryer where they literally have an open flame and a fan blowing stuff, then obviously that doesn't. Yes?
Why is it called lagging?
Why is it called lagging and leading? Okay. So lagging and leading has to do with the phase of the current with respect to the phase of the voltage. So for a lagging power factor, the current lags the voltage. And for a leading power factor, the current leads the voltage. Okay. For power factor measurements, it's always current with respect to the voltage. There's actually a simple mnemonic device to remember that, okay? It's called Eli the Iceman. So in Eli the Iceman, the L is representative of the inductance. E is short for electromotive force, which is just a physics way of describing a voltage. It's really all it is. Why are you guys smiling?
Our physics teacher went on a 20-minute rant about physics professors, they know better.
So electromotive force, all voltages are not electromotive forces. That's an error. Yeah. No, I take that back. All electromotive forces are not voltages, but all voltages are electromotive force. So what an electromotive force does is it pushes a charged particle around a closed path, which is exactly what voltage does in a circuit. But an electromotive force might also be representative of the voltage created by compressing a piezoresistive crystal, or the voltage caused by a chemical reaction or something like that. So they're technically different, but yes, we EE people are lazy, and so we just say they're the same. I fundamentally understand that they are different. I don't care. Okay. So E is representative of electromagnetic force, which us lazy engineers call voltage, and I is representative of current. So so in that Eli portion, the I comes later than the E, so the current lags the voltage. In the Iceman portion, which is good for capacitors, that's what the C stands for, I comes before E, so the current leads the voltage. So that is one way to remember it. I didn't learn that until I was in graduate school, actually until I was teaching Circuits 1 with somebody else who had gotten their undergraduate degree in India, and it was like, oh, I just remember it this way. I remember it from the sign of the phase angle. The sign of the angle theta S tells me everything I need to know about whether my load is inductive and therefore whether my power factor is leading or lagging. But that is definitely handy, so it's stuck in my brain too. Any other questions with regards to power factor? All right, so let's now cover the power triangle. So in my opinion, This is where everything kind of start to click, or at least I hope so. All right. So let's say that we have a generic load, Z is equal to R plus JX, where R is the resistance and X is the reactance, and we are assuming for now that both are positive quantities. A power triangle for this load would look something like this. So this S represents the complex power absorbed by the load, mathematically defined as, again, the RMS phasor voltage times the complex conjugate of the RMS phasor current. The projection of S onto the real axis is the average power, and the projection of S onto the imaginary axis is the apparent power. So we can see very easily that complex power is P average plus JQ, right? Our complex power has a magnitude, S, and it forms an angle with the positive real axis, giving us our apparent power and our power factor angle. So our power triangle really tells us all that we could possibly want to know about the behavior of a particular load, okay? It tells us the average power, it's got the reactive power, it's got the apparent power, it's got the power factor angle by which you can easily determine the power factor either using that angle or the apparent power, assuming the average power over the apparent power. It's got all of the information just buried inside of it. So for me personally, whenever I am analyzing a steady state sinusoidal circuit for any power quantity, I don't care whether I'm asked for average power or reactive power or anything like that. I calculate the complex power and then use that to get the quantity that I want. Because that way I only have to remember one simple equation, which is just multiplying two numbers together to be able to get literally every quantity that I could ever care about, okay?
What is the S complex power? What
Yes.
is the normal S?
Apparent power. So if you prefer to write it as AP, go nuts. I don't like that symbol because it's two letters. That's literally the only reason I don't care for it. One thing that is very important and can save you guys potentially a lot of time in calculations and stuff like that is recognizing that our polar angle theta S is the exact same as the angle of the impedance that we're performing our power analysis on, right? Because it is by definition theta V minus theta I, which is the angle of an impedance as well. We talked about that a couple of class periods ago. All right, so as I said before, this simple graphical tool contains all of the information provided by the numerous mathematical relationships that we developed previously. Additionally, further information about the behavior of the load can be inferred by looking at the power factor angle theta S. So if theta S is equal to 0 degrees, then our power factor is exactly equal to 1, and we know that the load is purely resistive. which means R is greater than 0 and X, its reactance, is equal to 0. If 0 is less than theta S is less than 90 degrees, our power factor is lagging, and the load is inductive, meaning that R is greater than 0 and X is greater than 0. If theta S is exactly equal to positive 90 degrees, our power factor is 0, and the load is purely inductive. Nope, inductive. Where R is equal to 0 and X is greater than 0. If negative 90 is less than theta S is less than 0 degrees, our power factor is leading. And the load is capacitive. So we would have R is greater than 0 and X is less than 0. And finally, if theta S is equal to negative 90 degrees, our power factor is 0 and our load is purely capacitive. R is equal to 0 and X is less than 0. Now, I want you guys to notice that my definition for leading and lagging power factor based on this angle is different than what we just previously discussed in the last section, specifically on power factor. So previously I said that if the angle is between 0 and 180 degrees, our power factor is lagging. And if the angle were between negative 180 degrees and 0, we said that the power factor is leading. These restrictions are forcing the resistance quantity to be positive, okay? Which is what we are going to observe in the overwhelming majority of cases. We only have to expand that definition to include everything from 90 to 180 and negative 180 to negative 90 if we are allowing resistances to be negative, which isn't going to happen a whole heck of a lot. Does happen to happen in these fluorescent lights in this room, but doesn't happen a whole heck of a lot, okay? Because of the way that the plasma is generated inside of that. It's got a little bead of mercury in each one of those tubes. You hit a very, very high DC voltage and it vaporizes the mercury, which causes the phosphorescent coating on the inner side of the tube to glow. But negative resistance isn't encountered very much at all, except in the lights that we have everywhere around. So, yeah, so, all right, so power triangle, everything seem okay? Anything seem wild or crazy or too difficult or anything like that? Yes, sir. If they were of the same magnitude, yes. So Does current flow through a short circuit? Absolutely. But a voltage drop across it. So you get into an issue of it being a true short circuit, meaning that there is really no resistance whatsoever. That's never going to physically happen, right? You can never completely balance anything like that out. So if it were truly a short circuit, meaning that it had a resistance of exactly 0, then yes, you are correct. There would be no voltage drop and there would be no current flow. But even if there's 1 nano ohm of resistance, current will flow, or a voltage drop is required. Either current will flow, generating a voltage drop across it, or vice versa. So I mean, like the lights in this room, they definitely have some resistance associated with them because there are wires connecting to the end caps of the fluorescent tubes and all that kind of stuff. But I think the negative resistance of the bulb itself, or the mechanism by which light is emitted from the bulb, is significantly larger than the series positive resistance of the wiring. Yeah, you wouldn't. I can't think of any practical place other than some kind of weird, crazy superconductor type thing where you might actually see a resistance that is even very close to 0, other than like closer to 0 than a piece of wire, which to us, when we're looking at things on the large scale, you know, a couple of milliohms seems like it's nothing, but can actually be pretty large in specific applications. But for like a superconductor where you've got a chunk of material at very close to absolute 0, I'm sure that you can get resistances that are much, much closer to 0, but practically that's not going to happen. Like that's a very specific experiment in a very fancy lab, not you plug it into that wall outlet, you know?
Micro sounds like a problem for
Yeah, and you'll run into micro ohm scale issues in the development of integrated circuits and all that kind of stuff too. We only have 15 minutes left. I do have other stuff I'm supposed to talk about. So like in an integrated circuit, like not all of you are going to have to take this specific class. It's a senior level class on literally designing integrated circuits and all that kind of stuff. But we use a program called Electric VLSI to lay out all of our transistors and wires, connecting everything and all that kind of good stuff. Because the amount of metal that's deposited to create a wire is of a uniform thickness, we wind up dealing with a quantity that's called sheet resistance. So the sheet resistance is really just resistance divided by its thickness. And so for a particular amount of surface area of metal, you get a resistance. And when you put some of those squares of metal together, you can create larger scale resistances and all that kind of stuff. The resistances that we're dealing with in that class are typically on the order for metals and things like that, have a sheet resistance of about 100 milliohms per square or smaller, depending on whether it's the metal 1 layer, metal 2 layer, metal 3 layer. The thicker it is, the smaller the sheet resistance is and all that kind of good stuff. Now you would think that because those resistances are that small, they don't really come into play, but because everything in an integrated circuit forms a RC network, because you have, even if you just have a section of wire, it forms a capacitance with a substrate, which means that everything is fed through a low pass filter. And so even those very, very small resistances start to matter because they limit the switching speed of your transistor architecture and all that kind of stuff. So they'll come and bite you in the ass quicker than nanosystems classes if you're not paying attention, I guess is what I was getting at. Okay. So we have developed all of this stuff. Now let's develop some simple alternative relationships. So these are just shorthand things that I like to use to get through problems a little bit quicker. They are all based off of just our fundamental definition for complex power and Ohm's law. So it's not rocket science or anything like that, okay? So alternative relationships. So all of these fundamentally start with the following two relationships. S is equal to V RMS phasor times I RMS phasor conjugate, and Ohm's law, which says that V RMS phasor is equal to I RMS phasor times Z R impedance, okay? So relationship number one, S is equal to V times I conjugate. Well, we could express V as I times Z, and we multiply that by I conjugate. What we get is I RMS squared, which is the result of multiplying our RMS phasor current time its multiplied by its complex conjugate. That gives us the magnitude squared times the impedance Z. Which we can write as I RMS squared times the magnitude of Z. I shouldn't put a hat over it because it's not a phasor. With an angle of theta Z, if we're looking at Z as a polar complex number, or this becomes I RMS squared R plus J I RMS squared X. If we look at Z as a rectangular form complex number. So if you wanted to know the resistive losses of a transmission line through which you knew how much RMS current was flowing, you can actually determine that quantity without actually knowing anything regarding the phase angles or anything like that. Okay, so it's just a shorthand notation for getting some specific things, particularly power when you only know the current. Relationship number two, we have V times I conjugate. Now we're going to substitute in V over Z, and we do the complex conjugate here. Okay. So this is going to give us V RMS squared divided by the conjugate of Z. Okay. So this is something important that I want to point out here. We have the complex conjugate of a fraction, which means we need to take the conjugate of the numerator and the conjugate of the denominator to do that operation correct. So we have V multiplied by its complex conjugate, giving us the magnitude of the voltage squared, divided by the conjugate of the impedance. And from this, we can express it as V RMS squared over the magnitude of Z with an angle of theta Z. Now you might be thinking to yourself, why isn't it an angle of negative theta Z since we took the conjugate? Well, the conjugate is in the denominator. So we have something angle 0 divided by something angle negative theta Z gives us angle positive theta Z in the numerator. This is where Z was equal to Z angle theta Z. And in rectangular form, this becomes VRMS squared over the magnitude of Z squared times R plus J VRMS squared times the magnitude of Z squared times X when C is equal to R plus JX. So definition number 2, not used a whole heck of a lot, but can get important in power factor correction, actually. So the last thing that I want to introduce you to you today is that we can develop some relationships for resistors, capacitors, and inductors explicitly. Okay, so for a resistor, S sub R, since we know that a resistor has a assumed positive value for the resistance and a 0 value for the reactance, we know that the imaginary part should be 0. And so we just have I RMS squared times R, or V RMS squared over R. For a purely inductive load, meaning the resistance is 0 and the reactance is positive, we're going to have J omega L times I RMS squared, or J times V RMS squared over omega L. And from this, we can easily see that inductors absorb reactive power, right? We know that we're dealing with only reactive power because there's a J in front of both terms. And for purely capacitive loads, S sub C, we have negative J times I RMS squared over omega C, which is the same as negative J omega C times V RMS squared. So just to recap, resistors absorb average power, inductors absorb reactive power Q, and capacitors supply reactive power Q because they absorb negative Q. Okay. And this last bit right here actually leads us directly into power factor correction and why we use capacitances to correct exceedingly lagging power factors. But that is for Wednesday. All right, so Wednesday, I'm going to work like an example problem or two talking about the different relationships that we've developed for all this kind of stuff because we ran out of time. That'll take maybe half an hour or so, then I'll spend the other half an hour or so talking about power factor correction, and we will be finished with single phase steady state sinusoidal circuit analysis. You guys probably didn't know you were doing single phase, but technically you have been. Like I said last week, we will not have class on Friday. So when we kick off on Monday the 10th, that starts our 3-phase power section, and that's what we'll be doing until the end of class. All right, see you guys later.